When we have an inner product space, we have the concept of inner product. Now we introduce the notion of orthogonality. So we say x and y are orthogonal, and we use this notation like x is perpendicular to y, even only if the inner product space that you define on such space is equal to 0. Okay. And when you have that notion of being orthogonal, for example, in Rn, obviously these two guys are orthogonal, right? And but this concept is not just limited to vector space Rn. Any inner product space can be explained by this concept. Okay, we're gonna have an example here. Can you check real quick that if you use the conventional inner product on each of the following space, please verify that these two vectors are orthogonal. So x transpose y, suppose this is x and this is y. X transpose y is going to be 1 times 1 plus 0 plus minus 1, and it is 0, right? Obviously. If we use, let's take a look at the second example. If we just use the inner product that define on the space of matrices is trace of y transpose x. So please verify the calculation. You compute y transpose x and you just take the trace. The result is going to be 0. Okay. I hope it's not hard. Um, in this example, is a space of continuous function on the interval 0 to 1. Suppose this is fx, this is gx. Now, if we use the typical inner product again, that is the integral of fx gx dx from 0 to 1. Okay, can we move? Okay. We can show that for this choice of function, integral from 0 to 1, x times 4x squared minus 2 dx. Okay, that's going to be the integral of 4x cubed minus 2x dx from 0 to 1. So that's going to be x fourth minus x squared from 0 to 1. And that's going to give you 0. So Um, so from this result, in this example, I would like you to take a look that when we talk about the space of function, one function is linear in x, another function is quadratic, right? So now we have this concept that, oh, these two functions are orthogonal. They are orthogonal in the sense that that we use this inner product to define the degree of being perpendicular. Okay. Once we know the concept of orthogonal between any two entities in the inner product space, now let me come back to the new concept of orthogonal complement. Suppose we have a subspace S of V. V is a whole vector space. S is a subset of V. S is a vector space itself. Okay. We're gonna call S perp from perpendicular, and we use this notation S perp. S perp is gonna be a set of any vector x that orthogonal to all S in S. Okay. For example, for example, mm-hmm, you that my S is a span of any vector A. All right. So how my S look like? My S is going to be a line in a space of Rn. Any vector that is in the same direction as A is a member of S. Okay. So what would be the S perp from this notion? S perp, it would be any vector x that lies on this direction or this direction. Any one that is perpendicular to A. All right, that's it. Now let's take a look at some of the now it's the other way around, okay? This is a new example. My S just says that, okay, my space S is any x that A transpose x equals 0. How does this space look like? It's gonna be in Rn. It's gonna be a hyperplane, right? A hyperplane that is described by a normal vector A. Okay, and this hyperplane has to be has to pass the origin. And what we can see is from the translation term. And the reason why it has to pass the origin is for S to be a vector space. Okay. Otherwise, it's not. Okay. So it is obvious from this example that, okay, the definition of a superb orthogonal complement is any one is a collection of any vector that is perpendicular to all the member in S. When all the member in S is the vector described by the plane, right? Anyone on the hyperplane is a member of S. So, and that hyperplane itself is parameterized by a normal vector A. We know that we call it a normal vector because the normal vector A is perpendicular to anyone on the hyperplane. So in this example, therefore, S perp is a span of A. Now let's take a look at more example. Now let's talk about the space that's spanned by 1, 0, 0. Okay, suppose x1, suppose x2, x3 here. And the span of 1, 0, 0 would be any one on this line. Okay, so the vector component, the second and the third component are all 0. Okay, so it's a line here. So if we just characterize, so as perp is going to be a set of x in R3 that my x, all right, is perpendicular to S but equal to 0, right? For all S in big S. But how would I describe any small s? If my S is in the subspace S, my S is just a multiple of 1, 0, 0, right? So it's enough to say here that my X would be someone that inner product with 1, 0, 0, and then give it to 0, right? So in this case, when you parameterize it, you see that my X that is going to be a vector in S perp, my X is just that. How would you expand this inner product? It's going to be x1 plus 0, right? So it means that my x must have the first component as 0, and the second one and the third one can be any arbitrary number. Okay, so how can you describe it? How can you give a general form? So it's going to be x2 0 1 0 plus x3 0 0 1. Okay, so basically these two vectors form a basis for your S-perp. So that's why your S-perp is a span of 0, 1, 0 and 0, 0, 1. So, okay, by this example. It's a nice example, nice exercise to show that S-perp is a vector space. In order for you to show that, remember the concept of vector space. You must show that if you pick any y in S perp and you pick any scalar in S perp, a vector space must have the property of closed close under addition and close under scalar multiplication. So you need to show that alpha x plus y also belong to S perp. Okay. I hope it's not hard to show this. Now let's see some just like uh so once you have saw that you have seen this yourself that S perp is a vector space, it just clearly explained this step in the previous example that I have characterized my S perp that any x in my S perp is going to be in a general form like this, right? And what you can write is that it's a span of these two vectors. So this is to confirm, right? When you have a span of any two vectors in Rn, we know from linear algebra that this is a vector space itself. So it's confirmed to this general fact. We have the last example as a set of matrices. So I give you my set S. It says that my set S contain only the matrix that the 1, 1 and 2, 2 elements are 0 and 1, 2 and 2, 1 elements are free. Okay. How long is it? Has it been 11 minutes? Okay. So my S perp is gonna be any vector B in R2 by 2 by the definition, where if I use the typical inner product, that's gonna be the trace between, okay, let me first call it. So my B inner product with A is gonna be 0 for all A in S. Okay. And now I'm gonna use the fact that my inner product is trace of A transpose B. Okay. Now I'm going to take, again, what you can do is first you take a general form of A, or you can think of this way. You can think of first, I can find a basis for S first. If, I mean, from this example, it's obvious that two basis vectors are 0, 1, 0, 0, and 0, 0, 1. All right. This is the basis for S. So if you want to look for matrix B that is orthogonal to any A in S, is only enough to what? To say that this B has to perpendicular to, let me call it A1, A2. Suppose these are two basis matrices. So is it only enough that you check only the orthogonality condition on the basis? Right? I hope that you find it obvious because any A can be written as a linear combination of A1 and A2. So any A can be written as alpha 1 A1 plus alpha 2 A2. So if inner product of A1 and B and inner product of A2 and B is 0, isn't that obvious that inner product of A and B is 0 as well for any A? Can you do this real quick? I hope it's clear, right? Because inner product of A and B would be by the linearity of inner product, because that's going to be alpha A1B plus alpha 2 A2B. Okay, so you can show it quickly that is obviously 0. So in order to characterize my set, the set S perp in this example, is only enough that I check orthogonality condition between B and the first basis matrix and B with the uh, second matrix. Okay. So so first, if I take B as a general one first, B11, B12, B21, B22, all right. If I multiply with, what I'm going to do is I'm going to do on A1 first. A1 transpose B is going to be 0, 1, 0, 0 times B, right? So that's going to be 0, 0. That's going to be B11, B12. And then when I take the trace, what do I get? I get B12 equals 0. Okay. I hope you do the same. I hope you do the same. So the second condition would be A2, right? So I'm just gonna delete it, all right? A2 transport would be 0, 0, 1, and 0. And that's gonna be B21, B22, and then 0, 0. But now you're going to have, so the trace is gonna be this one, and next you're gonna have B21 equal to 0. That's why the general form of S perp is going to be a set of any B that B12 is 0, B21 is 0. So it's a set of a diagonal matrix eventually. So from this result, you can say um, a matrix A has always diagonal entry as 0, and the off-diagonal term are free. That is, that matrix is always perpendicular to diagonal matrix. Hmm. Okay. Um, Last note on this topic. All right. Once you have understood the concept of S and orthogonal complement S perp, we have orthogonal decomposition theorem. So suppose M is a sub. So let's give example of Rn first. The space of Rn admits the orthogonal complement is basically means your Rn space. It can be decomposed as M, which is any subspace of M with M perp. Okay. Take a look at this example. We have seen that span of 1, 0, 0 is perpendicular to this space. Let me draw this again. X1, X2, and X3. Okay, so you have S as the any line on the X1 axis. Okay, but for S perp, S perp is going to be any vector that span. I hope that you understood that you understand my drawing, because this says that you span any vector of 0, 1, 0. Let me call it E2 in short. This is E3. So E2 is going to be a vector in a x2 axis, and E3 is going to be any vector in x3 axis. So the spans of these two guys is going to be any one on this plane. So it's going to be the plane. So I should have so it's going to be any vector on x2, x3 plane. And obviously it's a perpendicular to S, the line, the yellow line. Okay. So what I mean by admitting Rn is admitting orthogonal decomposition, it basically means that you can decompose R3 as S direct sum. This is our notation, direct sum with S perp. And what direct sum means is that you can represent any y in Rn as a member M in big M plus M tilde in M perp. Okay. If we apply that the orthogonal decomposition to this example, so any y, you can represent any y1, y2, and y3. So you can write it as, do I have enough space? As y1, right? Plus 1, 0, y2, y3. And then you can see that these components belong to S and the other one belong to S perp. Okay. Um, hmm. The concept of inner product, not only that it allows us to talk about orthogonality of two guys, two entities in the vector space, is actually the origin of many useful results that we have seen in the past. Now, I think most of you have heard the Pythagoras theorem and parallelogram law. Okay, let's make a short proof of this well-known result. Now, I'm talking about any x and y with in any product space, and the norm of y, the nation norm is the induced norm. So the result in this page not only applies on a vector space Rn, but it can be anything, any inner product space. So we're going to start with the norm square of x plus y is the inner product of x plus y with itself. You expand it xx, yy, right? Yx, xy, okay? Now you compute the norm of x minus y, that is the inner product of x minus y with itself. You do the same, expand, but now you're going to have the minus sign here, okay? So, Pythagoras theorem, okay, Pythagoras theorem. Pythagoras theorem says that this side square is going to be the sum square of the two sides, right? Now, let's take a look at the first result that we have derived. If x and y are orthogonal, these guys go to 0, right? And then left-hand side is norm of x plus y square. And this is norm square. This is norm y square. Okay? This is how we derive Pythagoras theorem. Next, parallelogram law, okay, is given by taking a look at these two, okay, and we basically add these, we got the right hand side, and when we add this and this, these things cancel up, and then now we get 2 times norms of x squared, 2 times norm of y squared. Okay, so parallelogram law just tell us about the relationship of these parallelogram. Suppose you have x and y, right? And uh, x plus y is going to be this vector, right? And x minus y is going to be the red vector. So is the law that says the width of this side plus the width of this side, the sum square of it is going to be 2 times this side squared and this side squared. Um, so let's cut the topic. Let's stop here, and then in the next slide, next video, we will talk about one of the important concepts in inner product space. So this is a transformation called orthogonal projection.